So we introduced parametric equations last time. So let's talk about how we can use those parametric equations. The primary use of them for our intensive purposes, and it's not the only use, is mostly for projectile motion. It's when you want to define two things in terms of time. Most of the time with parametrics, we're going to be using it to add the extra addition of time. So with projectile motion, it's traveling a horizontal distance, it's traveling a vertical distance, and it's traveling over time. So there's three things happening. So we have the horizontal, which we usually define as x, we have the vertical, which we usually define as y, and then we have time, which we usually define as t. So if you throw something, it has a parabolic motion. So we have this parabola. We've got x here, we've got y there, and we've also got t as it goes along. And time is progressing the entire time. So it behaves like this. So that's the path. So we could physically graph the path using x and y. We could graph the height of it in terms of y and t, and we could graph how far it goes horizontally in terms of x and t. Now, each of those functions is going to be a little different. If we're doing the actual path of it, it would be a quadratic. So it would be y equals something in terms of x, and the x would be a square term. If we were doing the height over time, it goes up and then it goes down. Again, it'd be a quadratic. So either equation of y, whether it's in terms of x or in terms of y, is going to be a quadratic. But x, it doesn't go up and go down. It just keeps going. X over time, you start here, and then you keep going and going and going and going and going, and then you end here. So x in terms of time is going to be a linear function. So we've got three functions to choose from. We've got the two parametric equations that model the actual path of the ball. Now, when you actually throw the ball, it basically shoots out straight, but then gravity gets a hold of it. So it's affecting, if there was no gravity, if we were in a vacuum, it would just follow along a vector, which we talked about briefly. So as it follows along this vector, we've got the angle of the vector, and then the magnitude of the vector would be the speed of the release, or velocity of the release. It doesn't really matter for our intensive purposes, but the speed that the object is launched is the magnitude of the vector. So our vector, it's the magnitude, and the horizontal component, it's the cosine of the angle, and the vertical component is the magnitude times the sine of the angle. So horizontally, this is that, and vertically, that distance is right here. These are going to be used for our equations, for our parametric equations. Those are going to come into play for how we get our parametric equations. For the horizontal piece, the x equation, that came from this component, the speed times the cosine of the angle of launch. So for our horizontal piece of x in terms of t, it's going to be a linear function, we said, And the slope of that line is that initial speed, that initial velocity, times the cosine of the launch angle, times t. And then the intercept is just where you're starting horizontally. Most of the time, this is just going to be 0. Most of the time, that term's just going to be 0. Not, I mean, sometimes it could be like, oh, you're 20 feet away from the tree, and then you throw the ball, and how far away is the ball from the tree? Then your x would be 20. But most of the time, that's going to be 0. Very, very few times will that be 0, because if you throw the ball with at 0 feet per second, then you're not throwing the ball at all. And also, you should practice more. Now, if we want the vertical we said was a quadratic. So it's y of t. So we're going to have a t squared term. And we're going to have a linear term as well. And the linear term is going to behave very similarly to how the linear term behaved in the horizontal equation. So it's going to be our initial velocity, except since it's vertical, it's not cosine, it's our sine of the angle, plus t. And then we have our initial height. The initial height, if you're not given an initial height, like say someone threw a ball and they don't tell you how tall that person is, you just assume that it's 0. We know it's not 0 if we were doing a word problem where the stakes were higher. Like if we were actually trying to launch something into space, we would find the exact measurement of this, because an error of a few inches could be the difference between Apollo 11 and the Challenger. So it's different things. So if the stakes are high, this is important. If it's just a word problem in this class, stakes aren't that high, especially now that's credit, no credit. So if we don't give it, that's just going to be 0. So now we need this. So if you remember from physics, the coefficient of your t squared was the acceleration. Well, the acceleration in projectile motion is your gravity, and this is going to be 1/2 gt squared. All right. Next year, you'll actually learn why it's 1/2 gt squared. It has to do with derivatives and integration. But right now, just trust me, it's 1/2 gt squared. So, g is either negative 9.8 meters per second squared or negative 32 feet per second squared. We're in America, so we're going to do this one more often. But if you ever do go into a traditional science community, the science will be translating across borders, so you'll probably do that one more often. But we're probably going to do this one, largely because I prefer to use negative 16 than negative 4.9, just personally. That's just a personal preference. All right, so we've got our equations. So let's say we had a problem. I wrote one out before. Mr. Olson throws a baseball at an angle of 55 degrees with a velocity of 64 feet per second. How long will it take for the ball to hit the ground, and how far away from Mr. Olson did the ball land? So the things we can get from this right away is we know our theta is 55 degrees, and we know our initial velocity is 64 feet per second. Since it's feet per second, our gravity is going to be feet per second squared, so it's going to be the negative 32 feet per second squared, because we want to maintain common units. We're not told anything about his initial position, so we're going to assume that x sub 0 is 0, and we're going to assume that y sub 0 is also 0. So we've got these three pieces of information, and now we can write equations to model how this is working. If we want the horizontal equation, it's x of t equals the velocity, which was 64. Oops, that's not 6. Let's try that again. 64 feet per second times the cosine of the angle times t. So that's our horizontal equation. So at any given time, we can find out how far away from the initial position the ball is. For our vertical, it's 1/2 gt, gt squared rather. So it's negative 16t squared plus our initial velocity times the sine of the angle, and then plus our initial height, which we're not told, so we're assuming it's 0. So we've got these two equations, and if we wanted y in terms of x, we could just isolate t in that first equation and then substitute it in. So if we isolate t, that means t equals x over 64 cosine 55. And we can substitute that in. So it's negative 16 x squared. 64 squared is 4096. Cosine squared of 55 plus 64 sine 55 x over 64 cosine 55. And we can simplify this, make it a little easier. 16 goes into 4096. I want to say 256 times. Hold on, I got my calculator here. Pretty sure it's 256, but I don't want to be wrong. Yeah, it's 256. So y of x equals negative 1 over 256. 1 over cosine squared is secant squared of 55 x squared. Then the 64's divide off, and sine over cosine is tangent. So we could have that equation to model the actual path of the ball. How far, if it's 12 feet beyond where you were standing, how high is the ball? That's what this would represent. So we've got our equations. So now we can use those equations to go back and answer our actual questions. Our actual questions were, how long did it take for the ball to hit the ground? So if we're talking about hitting the ground, we're talking about height. And the height of something hitting the ground is 0. And we're looking for how long. So we're looking for the time when the height is 0. So we're going to be using our vertical equation. So let me just rewrite our equation. Y of t equals negative 16t squared plus 64 sine of 55t. And we want when the height is 0. So 0 equals, and we can say, factor out 16t, leaving us with t minus 4 sine of 55. So, well, t equals 0 there. That's our initial position. So that's not the one where it hits the ground. This factor is going to give us where it hits the ground. So at time equals sine of 55 seconds is when it hits the ground. That's approximately, I don't know what that is off the top of my head. So 4 sine of 55 is 3.28, approximately 3.28 seconds. So that's the hang time of the ball. Now, the second question, it asks us how far away from the Mr. Olsen did the ball land? Well, if we're talking about how far away from it did the ball land, that's going to be our horizontal distance. Well, we have two things with horizontal distance. This one's a lot more messy. We could set y equal to 0 and solve that one. Or, since we know the time, we could just plug in that time into here. So x of t equals 64 cosine of 55t. So t when it hits the ground is 4 sine of 55, or 3.28. I'm going to do the 4 sine of 55. So 64 times 4 is 256. Cosine of 55, sine of 55. And again, I don't know what that is off the top of my head. So 256, cosine of 55, sine of 55. I'm in degree mode. So it's approximately 120.28. 120.28 feet. All right. So there we go. So that's how you can use parametrics to work with projectile motion. All right. Have fun.